the last thing that I want to introduce now in this chapter on integrals, domains, and fields is actually something that relates all the way back to rings. And that's the characteristic of a ring. So let's suppose that R is a ring with unity. The characteristic of the ring R is the smallest positive integer n for which the sum of n ones is 0. If no such positive integer exists, then we say that R has characteristic 0, as opposed to what you might think it would be, which would be characteristic infinity. We're going to call it characteristic 0 instead. So to start out with some examples, the integers, rational numbers, real numbers, complex numbers, these are all rings. They all have a unity, which is the number 1. And each of these rings has characteristic 0 because no matter how many times you take the number 1 and add it to itself, you're never going to get back to 0. You're just going to get numbers bigger and bigger and bigger. So this is an example of the case where no such positive integer exists, and all of these rings have characteristic 0. Conversely, if you're working in Z mod n, you can take the unity 1 and you can add it to itself n times. And then what you're left with is the number n, which is thought of as 0 in Z mod n. So it is possible in Z mod n to take the unity 1 and add it to itself a certain number of times and end up at 0. And it's pretty easy to convince yourself that n is the smallest number for which this is true, and that makes the characteristic of Z mod n n. Similarly, it can be a little bit confusing when you work into matrices, since the ones and the zeros are sort of different. But let's suppose that you're working with the ring m sub k of Z mod n. So you're looking at k by k matrices where all the entries in the matrix come from the ring Z mod n. Now the unity in this particular ring is the identity matrix, which has 1s all across the diagonal and everything else is 0. If you take that identity matrix and you add it to itself n times, just like the Z mod n example, you're going to end up with a matrix that has n's all along the diagonal and zeros everywhere else. And because we want the entries in our matrices to all come from Z mod n, we're going to reduce those n's to zeros. And so we see here again that it's possible to take the unity of mk of Z mod n, add it to itself a certain number of times, and get to the 0 element, which is the 0 matrix of mk of Z mod n. And the thing that's just sort of slightly interesting about this example is that this is going to have characteristic n, no matter what the k is. So it doesn't matter the dimension of the matrix. What matters is the ring from which you took your entries to be a part of. And so what we've done here is I gave you some examples of infinite rings that had characteristic 0, and then I gave you 2 different examples of finite rings that had a finite characteristic. You can actually do something a little bit more interesting. You can find infinite rings that happen to have finite characteristic, and I'd like to leave this for you as an exercise, just to get your hands dirty with playing with some examples of characteristic and playing with some more examples of a ring. Now, something that's kind of interesting and fun that you can do with this definition of the characteristic of a ring, or maybe just as an example to show how things work differently in the world of things with finite characteristic. We're used to the integers, which are characteristic 0. What if we switch to a ring that has finite characteristic? And so the lemma that we're going to prove today is that suppose R is a ring with finite characteristic p, where p happens to be a prime number, and let's suppose that a and b are any 2 elements of the ring R. Then it's true that when you take the quantity a plus b and raise it to the pth power, that you get a to the p plus b to the p. Which is funny, we're used to this failing horribly in the integers. This is something that always breaks my heart, and I say it's one of the 3 unforgivable mathematical mistakes, is when you take something like in a calculus class, you take x plus y and you square it, and you say that that's x squared plus y squared. That just breaks my heart. It's x squared plus 2xy plus y squared. However, the reason that it's equal to that instead of x squared plus y squared is just because of the fact that when you're working with real numbers, like you do in a calculus class, you have characteristic 0. If you had been working in a ring all along that had characteristic p, then all of those people would have been right way long ago. So here's the proof, and the proof is a little bit fancy, but we're going to walk through it anyway. So what we're going to do here is we're going to first apply the binomial theorem. So we're going to take this quantity, a plus b raised to the pth power, and we're going to expand it out term by term the way we're supposed to according to the binomial theorem. So the first term you get in this expansion is a to the p, and then you're going to have p copies, p choose 1, of a to the p minus 1 times b, and p choose 2 copies of a to the p minus 2 b squared, plus ... and so on and so forth, up until the very last two terms I have written here, p choose p minus 1, ab to the p minus 1, and then the last term is going to be b raised all the way to the pth power. However, if you were in my abstract algebra class first semester, on your very first homework assignment, I had you show by induction that if p is a prime, p divides p choose k whenever k is a number strictly in between 1 and p minus 1, when p happens to be a prime number. And so if you take a look at that, the first term, a to the p, and the last term, b to the p, they don't have any p choose anythings written down in this expression, but everything else that I have, p choose 1, p choose 2, every other term that I have in this expansion has a p choose k in it, where k is some number in between 1 and p minus 1. As the number p is just 1 plus 1 plus 1 and so on, a total of p times, and the characteristic of the ring that we're working with is p, we really have that this 1 plus 1 plus 1 plus 1, however many times, is the same as 0. So each one of these p choose 1, p choose 2, these p choose k terms, all of these terms in the middle are divisible by p, and p is really 0 in the ring R. Therefore, every single one of those terms in the middle of this expansion is something multiplied by a 0, and they all cancel away. And the only terms that are left are the a to the p term and the b to the p term, the terms at the very beginning and the very end. Now, I presented that proof and I kind of glossed through it a little bit, but really this was just for fun. I wanted to show you that there's a handful of message boards out there. If you go to Google and so say you're one of these people, these freshmen that's really confused in my calculus class, why isn't it the case that x plus y squared is equal to x squared plus y squared? Some people on the message boards will be really nice to you and they'll explain to you very calmly why it should be equal to x squared plus 2xy plus y squared instead. And then you get some people who are probably a little bit more like myself that will supply some nice sarcastic answers about how all you need to do is just change the characteristic of the ring that you're working with, and then their dream of freshman exponentiation will come true. So I've provided the link there for you for a nice, if you're looking for some of the very funny sarcastic answers that people give, now you're prepared to understand those sarcastic answers and give them yourself if you choose. Back to a little bit more seriousness, let's just cover a summary of the things that we've covered in this third part over the total of these 3 videos we've done. After studying these videos and taking a look at your textbook, as you always should, these are the things that I want you to feel comfortable with. I'd like you, first of all, to understand and know by heart the definitions of an integral domain, of a field, and of the characteristic of a ring. The next thing I hope is that you'd be able to provide examples of rings that are not integral domains, examples of things that are integral domains but that are not fields, and then examples of fields. So you should have something on this threshold. Here's something that's a ring. It doesn't happen to be an integral domain. Here's something that is an integral domain, but it doesn't happen to be a field, and then here's an example of a field. Having those examples at your fingertips is a good thing to have. The next thing that I would hope you'd be able to do is to provide some examples of infinite rings, both with characteristic 0 or with characteristic p. And last but not least, I'd like you to go over those nice properties that we talked about in the very first video and feel comfortable with those proofs. And maybe take a look at some of the other examples. I have a list of exercises in your homework, and for you to complete in class some other nice types of properties that are going to hold now that we're working in an integral domain instead of an arbitrary ring.